Hydropower. Hydropower, or hydroelectricity, refers to the conversion of energy from flowing water into electricity. It is considered a renewable energy source because the water cycle is constantly renewed by the sun. One of the first uses of hydro energy was for mechanical milling, such as grinding grains. But today, modern hydro plants produce electricity using turbines and generators. The mechanical energy created by moving water spins rotors on a turbine. This turbine is connected to an electromagnetic generator which produces electricity when the turbine spins. There are two main types of hydroelectricity production: dams and run-of-river. Hydro dams utilize the potential energy from dammed water to produce electricity. A dam is a large barrier constructed to raise the level of water and control its flow. The elevation created by the dam creates gravitational force for turning the turbine when water is released. Some dams also contain an additional reservoir at their base where water is stored to be pumped to the higher reservoir for release when electricity is in demand. This is referred to as pumped storage hydro. The second form of hydroelectricity production is run-of-river hydro. Run-of-river still uses turbines and generators, but relies on natural water flow rates of rivers, diverting just a portion of the water through turbines. Because run-of-river hydro is subject to natural water variability, it is more intermittent than dammed hydro. There are various sizes of hydro plants that produce electricity. Large hydro, greater than 30 megawatts, small hydro, 100 kilowatts to 30 megawatts, and micro hydro, less than 100 kilowatts. The Hoover Dam in the United States is a whopping 2,074 megawatts, which is enough to serve 1.3 million people. Of all renewable energy sources, hydropower holds the largest share of worldwide electricity production. Hydropower has several benefits. It is a cost-competitive form of electricity, even though the initial building cost can be high. It is quite reliable compared to other renewable options and pairs well with other sources as it can be used as baseload power. In some cases, dammed reservoirs can also help with flood control and be a reliable water supply for communities. There are also some concerns with hydropower, especially when it comes to large dams. Damming a river has a major impact on the local environment, changing wildlife habitats, blocking fish passage, and often forcing people in riverside communities to move out of their homes. In addition, dam failures can be catastrophic, claiming the lives of those living downstream. Hydro plants are also not completely free of greenhouse gas emissions. As with most forms of energy, carbon dioxide emissions happen during construction, particularly due to the large quantities of cement used, and plant matter in the flooded areas makes methane, another greenhouse gas, as it decays underwater. That's hydropower.
From outside the station, we can't see the generators. If we approach, though, we can see the power lines or conductors that carry the electricity from the station to the national grid. Each power conductor connects to a turbine-powered generator inside the dam itself. Let's go inside the dam now and look at one hydro generator to see how the power is produced. The water from above the dam flows down through pipes called penstocks. Each penstock has its own headgate at the top to stop water flow for maintenance or during an emergency. At the end of the penstock is the scroll case. This curls around the turbine like a snail shell. It's designed to create a consistent pressure of water entering the turbine from all sides. Inside the scroll case is a set of vanes called the wicket gates. These control how water flows into the turbine. The wicket gates are controlled by an external governor system. This opens and closes them in response to conditions on the national grid. A high load on the system slows the turbine. The governor system reacts by opening the gates further to speed it back up. Conversely, it will narrow the wicket gates in response to low load on the system. Beyond the wicket gates, we can see the turbine blades. The blades are shaped to extract the most possible spin from the moving water. The turbine blades and the shaft connecting them to the generator are called the runner. We will expand this into its parts so we can see them clearly. At the top is the exciter. which gets a small DC power supply from a cable attached to an external controller called the Automatic Voltage Regulator, or the AVR. Below the exciter is the generator. The inside is a rotor, turned by the runner. The outside stationary part is the stator. This is made up of a set of 3 coils of copper wire called windings. On the rotor are a number of electromagnets, powered by the DC current from the exciter. If these are switched off, the turbine will be able to spin without generating any electricity. The magnet's poles on the outside of the rotor create a separate rotating magnetic field for each magnet. The magnets are lined up so that adjacent poles always have opposite fields to each other, north-south, north-south. As the rotor spins within the stator, each pole's magnetic field acts on the stator's windings. Each time a pole makes one full revolution, one pulse of AC power is generated in the windings and transmitted towards the grid by conductors attached to the stator. Because the stator is connected to the grid, it's important that the pulses are in time with the grid frequency. When the pulses are in time with the grid frequency, we say that the generator is synchronized. System conditions can push the stator's magnetic fields out of sync with the rotor. The difference between the movement of the stator's magnetic field and the rotor's is the torque angle. The rotor has many electromagnets on it, producing a consistent flow of power. The generator produces 3-phase power by using different conductors to carry the power generated along different parts of the stator, as shown here. This creates a 3-phase alternating current, which is represented by the sine wave.